So the goal is to compile to a 2D nearest neighbor architecture as well as possible. It's not the biggest algorithms, but the best compilation. So how do we imagine doing this? The goal is to allow people to specify their algorithm in whatever tool they like, and then find clear common pathways down to the physical level, and then run hardware or a simulator. So the main focus here is we want to get things into a ZX graph. So into PhysiX somehow. You can either go via Chasm or any one of the other tools here, and of course we're always looking to expand this graph. This is already just a sample of the ways to get data in. So start from your favorite. We will, however, definitely need to go through ZX graphs, and we'll explain those for people that haven't used them before. The kinds of hardware I care about, all 2D nearest neighbor. Worked for Google for over 10 years. That's all they build. That's where my background is. That's what we'll talk about today. This means things that have only nearest neighbor interactions, four-way specifically, nearest neighbor interactions, typical error rates around the 10 to the minus 3 level. That's our focus. So this hardware does exist, has been demonstrated. It can suppress errors. In principle, if you could make this big enough, it would be able to run things fault-tolerantly, with many caveats that building it big enough is very, very difficult to do and comes with all kinds of technical problems along the way. So we are not going to talk about those problems today. We're not going to talk about cosmic rays and calibration and all kinds of things that are very, very important if you actually want to build the big computer. We're just going to assume that we can focus on qubits that work and just use them. So first, some definitions. We're going to focus exclusively on the surface code. If you are already familiar with this, then this will be a very familiar picture. We are in the process of using slightly different sequences of gates. So if you have a look very carefully in here, you'll see this kind of standard Z, 1, 2, 3, 4, and N sequence. There's a new paper out just recently where we changed that so that the hook errors are diagonal, not perpendicular to the logical operators. Why would we do that? Because it means we can then tile a standard pattern everywhere in any orientation and not have weak directions in our code. So this slide is a little out of date. This is the link for what we want. But fundamentally, you have a grid of things. The blue ones detect bit flips. The red ones detect phase flips. You have this little chessboard of ways of detecting errors, and that's all the information you need to fix things. The bigger the square gets, the more you suppress your errors exponentially. And that's all. We are not going to focus very much at the physical level. What we want to do is instead define a three-dimensional version of this that is more powerful and simpler to work with. So what is this three-dimensional version? Every cube here represents D rounds of doing this quantum circuit. This quantum circuit is initialize a measure qubit, interact with the neighbors, and then measure out. Do it over and over again. One slice, this is D slices. And then we have these connectors that don't represent anything. They are just for visual expansion of the object, right? So this is a do-nothing operation, and then here's another D rounds of exactly this. So this is a 2D round memory experiment. So we want to just really get familiar with the 3D notation. Once you have these three-dimensional structures, the key insight, and really only thing I want you to take away from this slide, is you can slice it. So the bottom slice here is initialize all my qubits to 0. Here is the explicit circuit. Every slice here at layer B is a round of syndrome extraction. Over here is layer C. We are extending this surface with more physical initialization, and so on. Here is slice D. It's a big rectangle of surface code. Slice E, we are measuring these out in the Z basis, and now we're back to where we started, another version of slice B back here, but over here. So these diagrams are actually explicit quantum circuits with an emphasis on the explicit. It's not an abstract thing. You can take it, say, well, what's my code distance? What's my width across here, and then very systematically turn it into a very explicit gate sequence. So I don't want you to think that these are really theoretical objects. They're just a very, very abbreviated way of writing a quantum circuit. Here's another quantum circuit, all right? Now we've gone up and around and all over here. This is still just an identity gate. Data goes in, it gets taken away through a merry dance through space and time, data comes out. What we want to be comfortable with is the idea that, all right, we have a logical operator, Z logical operator, it's going to stick to Z walls, which are blue. And we can then just drag that operator around like a little band that goes all the way around and see that Z operator in becomes Z operator out. X operator in, drag it all the way around, becomes X operator out. If we're not changing the operators, we're not changing our data, this is an identity gate. And it's important to stress that we're not going to say, all right, well, this piece is some fancy initialization of a logical qubit. This is a Bell basis measurement. We're not going to do any of that, right? All we care is operators go in, operators come out. What happened to them in the middle? Nothing. So it's an identity gate, right? We don't talk about merging or splitting or anything. Just how does my structure guide my logical operators? So what about junctions? We're going to focus again, how does this structure guide logical operators? No more, no less. So if I look at this as, well, what does it do to a blue operator, a Z logical operator? Well, I can just drag it straight through. Or I could drag it to a different terminal. Or I could drag it down here. The key thing is that if I have a blue node, definition of a blue node is a junction with exactly two blue faces on the front and on the back. That has the property that blue logical operators must touch an even number of edges. They can come in, they must go out. Come in, go out. The opposite color touches every. All right, so if I have a red logical operator, X hits here, must go in all four directions. Same color, even number of edges, opposite color, every. And that is the only rule you need. Same color, even number of edges, opposite color, every. So you can reduce this three-dimensional structure to a graph node. And this is the way I look at ZX calculus, not as a great big body of theory in its own independent existence, a shorthand for lattice surgery, just a shorthand. So this is a very convenient shorthand. It even works down to single nodes. So this is a blue node, blue on the front, blue on the back, two faces, and I must go opposite color so it can touch every output, or one of them. I can't have a blue output. So this prepares a logical X eigenstate. This is a plus state logical initialization node. And here, last but not least, red node, two red faces, front and back, same color, even number of edges. And I stress even. You might say, why am I not saying two? Well, I could go out here, and then I could go around, and then I could come back down here. So I could highlight all of them. I can highlight an even number of edges. But if it's the opposite color, it must touch every. All right, so let's now extend that idea of operators in, operators out to our favorite two-qubit gate, the C0 gate. If you haven't seen this before, I wish you had, but the very basics, X on control goes to both, X on target goes straight through, and these relationships define what a C0 gate is. We don't have to talk about states in and states in, we can talk states out, we can talk about operators in and operators out. Completely equivalent, and for our purposes much more convenient because we have structures that map operators. So we want to move to the operator picture. Same deal with a Hadamard gate. We could talk about its effect on states, but it's better for us to talk about its effect on operators. Anything, any process that maps operators in these manners is this gate. So let's use these rules then to study a C0 gate. Let's consider this structure. So a blue node connected to a red node. Let's see what we get when we propagate operators through. An X operator, red, comes here. It's the opposite color. It must go to every output. This one is the same color. It touches an even number of edges. So this structure realizes the map of X on controlled goes to both outputs. Same here, blue hits same color, must hit even, goes straight through. That's our Z logical operator going straight through the control. X logical operator goes straight through the target because it's a red node, same color, even number. And last but not least, opposite color must hit every, same color, even. So these simple rules let us prove that this structure, a red node connected to a blue node, is a C0 gate because it maps all the logical operators in the right way and is all we need to focus on when we build things out of lattice surgery. So here it is. Here's a C0, here is a blue node, the control, connected to a red node, the target. So this is a C0, and so is this. Here's the blue node, here's the red node. And I can deform it however I wish, including rotated in space and time, because no matter how I draw it, it's always a blue node connected to a red node. This is topological quantum error correction. We care about the topology of the structure. And then, as mentioned earlier in the slides, I always have a systematic way to slice this into real circuits for real hardware. And indeed, we have used the tqec tool, which you are learning about, to run hardware at Google to do a logical CNOT gate. So this is a compiler all the way down to the gate level that works for hardware. Alrighty, so one more logical gate. We talked about Hadamard. Here it is. Here's how we draw it. So it's a way of connecting two nodes where you swap the logical operators. In practice, at the physical level, you would usually orient this in time, and it would just be a layer of Hadamard gates, but you can also do it in space. You just have stabilizers that have mixed type and convert logical operators from one to the other. So this is a perfectly good connector that does a Hadamard gate and can be oriented arbitrarily. All right, and let's use these. So we are going to compile this circuit. You'll notice it doesn't have a million qubits and a billion gates, right? We care about small things that you could, in principle, do in the near time on actual hardware. Why not? We'll take this computation. It happens to prepare a logical state for the steam code. Does that matter? No. It's a bunch of gates and we want to compile it very well. So what does that look like? First, we're going to convert every one of these gates into its ZX graph equivalent. And this is what it looks like. So our initializations in the Z basis become red nodes, because the red nodes, opposite color, output our blue logical operators. So that's what we get here, a bunch of red nodes to initialize. Here's our Hadamard gates, our CNOTs, and our measurements at the end, Z basis, right? Direct one-to-one correspondence. Now, if that's all we did, you would say, well, why would you ever use ZX calculus? That was completely pointless. But the beauty for ZX calculus is there are rules for what you can then do to it. One of those rules is the spider rule. And I look at it as something that comes from lattice surgery, right? Lattice surgery is topological quantum error correction. I can take this chimney here and I can move it over here because I am not disjointly deforming my colors. It's a smooth transformation, so it's allowed. Therefore, this, two different nodes, is equivalent to this. Whatever color I make here, provided they are the same color, I can merge and unmerge them. So you can look at that as a graphical proof of the spider rule. I don't need axioms of ZX calculus. I just need lattice surgery, and I just need to treat these things as an abbreviation. So we've added an extra rule. We also can use this Hadamard around a node to change its color. If you think about it, if same color goes straight through, well, if a blue node comes in, blue logical operator comes in here, it's going to become red, and then it will have the opposite behavior of whatever was seen from a distance. So it transforms the color of the node. So we are going to use these rules. Last but not least, there's an identity rule, which basically says if I reduce one of these nodes down to having just two edges, then both of these sides, red goes straight through and blue goes straight through, make it look like an identity gate. So if you only have two edges on a node, it's the same as an identity. It doesn't matter what the color of the node is, and you can just remove it. Those are enough to reduce what we started with, that big sting code computation, down to this graph. You merge all the red nodes together, merge all the blue nodes together, you turn your initialization and measurement, and it all collapses down to just this. And this is the power of ZX calculus, not because it's another way to write a circuit, because it gives you rules that let you compress things down to very compact graphs. Now, having done that, we don't want to undo our hard work. We want to directly realize with lattice surgery this structure. So here is a slightly rewritten version of that same graph. We used this particular rule. It's called the bialgebra rule. But frankly, you can prove it just by saying, well, if I take blue in here, right? Blue is going to go straight in. It's going to go through, because it's the same color, even. It's going to hit here, go to every. This one will go down here, and out that way. So a single blue in goes to both out. Single blue in, all right? You can prove it systematically that these do the same thing at the high level. So any garbage that you match in the middle can be replaced, so you can just prove things at the graphical level. So anyway, this particular graph is equivalent to this one using that on this piece. All right, so here's our little hourglass. That's how we transform this one into that. Turning it into lattice surgery then becomes a node-by-node progress. We just choose a node, and say, all right, here is a 4-way blue node, and then we draw it. And then we choose another node, all of its neighbors. Here is a 3-way red node, and we add them to the structure. And then we keep going until we have the direct structure. And the key thing is you no longer see the C0 gates. Where are they? They're not there anymore. What you have is a compact object that produces the stabilizer state that was the output of that circuit. Fundamentally, the circuit just prepared a 7-stabilizer, 7-qubit stabilizer state, the Clifford state. So just build the structure that supports those stabilizers directly, right? Don't think about gates. And then you can take your pick as to whether you slice it in time from bottom to top, left to right, whatever fits your computation best. If you want to deform a corner of it, because you don't really want to stick it out here, you want to make it go up, you can. You can deform it topologically as you wish. So that was a hand compilation. Go ahead, question.
Sorry,
Please.
For the black dots on your ZX graph, what do they represent? So
that's when we have not chosen what color. So if we have an identity that has black dots, it means it'll work for either color.
I see. So do they correspond to the input and output pipes on this diagram, or like?
So in this particular picture, you could, if you wished, to look at it as an input-output relationship, or for this particular computation, the framing was that all 7 of these are output, because we're preparing a 7-qubit state. So as drawn, the intended interpretation is this is 7 outputs, not an input-output relationship. But it's a good question. I mean, if we go back to a C0 gate, right? What is this? Is this an input-output relationship, or is it a structure that prepares a 4-qubit stabilizer state? Because you could look at it that way, right? Fundamentally, what these things are the stabilizers of a 4-qubit Clifford state, and it prepares them. Or I can look at these two as inputs and these two as outputs, and then it's a C0 gate. Or I could look at these two as inputs and these two as outputs, and it would be C0 the other way, because it's symmetric. Or I could look at any two of one down the bottom and one at the top as my inputs. These two could be my inputs, and these two could be my outputs. So there's a lot of flexibility. The fundamental thing are these correlation surfaces. How you use them is very largely up to you. Yeah. One more on that topic. This thing I said was an identity gate because I chose to look at this as an input and an output. If I preferred, I could have looked at this as a Bell state preparation circuit because it stabilizes a ZZ and XX. All right, good question. So this is a hand way of constructing. So we have tools. In fact, this is SketchUp, where you have a library of blocks and you can just drag them together, and then you can take the output of SketchUp and put that into tqec and get a quantum circuit that runs on real hardware. So that's one input that we're working on polishing up better and better as time goes by. The latest iteration is a custom 3D tool where you can just highlight a block and then just use the arrow keys, plus and minus, and go up, down, left, right, forward, back, and just add a pipe. It becomes very, very quick. No more click, drag, copy, anything that you do in SketchUp. So, our goal is to make hand compilation very efficient and actually produce real circuits that run real hardware. Go ahead, question.
I really want to understand this picture. So
sure.
On the left-hand side, you have 4 inputs and 4 outputs. If you read from left.
As mentioned, the framing of the circuit is a 7 output circuit. But really, it's a circuit that has 7 correlation surfaces. If you wish to look at it as an input-output, you can. My choice here is to look at it as a 7 output circuit, no inputs.
8 being the only input.
There are no inputs, they're all outputs.
All outputs.
It's a choice. If we go back to the circuit that we're compiling this circuit. This circuit has no inputs. It has 7 outputs, no inputs. Prepares a 7-qubit logical state.
Then the right figure is a pipe, so like I would.
Yeah. So what you're struggling with is where is time? But the point is this is a Clifford circuit. So I can rotate this arbitrarily in space-time, right? Clifford circuits on any quantum computer can be done in amortized no time, right? You can have your non-Clifford bit that then pipes into a big Clifford circuit that you do in the past, and then pipes into your next non-Clifford bit. So there's no reason for you to worry about time when we're talking about a Clifford circuit. If I go back to my CNOT gate, right, you could have time run up, but you could have time run down as well. You could have time run from inside to output. All that matters is the topology of the structure. Your data is going to get processed as a CNOT gate regardless. Yeah? Go ahead, Michael.
I guess ultimately you're gonna pick time direction if you want to use this compilation,
Yeah.
and then all of your outputs would have to go up in the direction. Right?
Well, if you have an output that's down, it's going to have to connect to something else.
Okay, but if you have the entire circuit, then
Yes.
and maybe you're going to talk about this, but it does seem difficult to incorporate non-Clifford things in this.
No, we will talk about that. Yeah, if we will definitely incorporate that. So, for the moment, one of the most canonical examples of being able to go backwards in time is your usual quantum circuit for a CNOT gate, right? It sort of implies that you have to do this, which is of course not true, because if you think of this as topology, right, I'm not going to draw the full three-dimensional structure and all the colors, there's no reason I can't do this, right? And conversely, there's no reason I can't do this. Just take the output and make it point that way. If that's convenient, I can do it. And I can add another effective CNOT gate here and do whatever I wish. It's all still going to work just fine. It will do the processing. Sure, eventually, as Michael points out, I might need to move my output this way, but I don't have to. There are many ways where a quantum circuit can be quite limiting when it comes to thinking about compilation and space-time volume efficiency. Because for Clifford, you don't need to worry about time ordering. Yeah. With this code, it makes it very explicit. You just need to worry about the topology of the computation and you'll get your answer. We'll keep moving. Go ahead.
Are there rules in assigning the node numbers here, like in the right?
No, you could start anywhere. So this is an example. And this particular hand compilation was after a number of different attempts of different orders of doing it and massaging the graph in different ways to just find a realization that is compact. All right? So this is no claim that this is optimal, but it's the best I could find out of a lot of effort of hand compiling. Yeah. This is an automated procedure. Same deal. The graph went in. We have a tool called topologic that then lays it out. And again, you can try different ways, try to make it better. The goal is, of course, to have automated tools that do as well as humans, right? At the moment, that is not the case. But of course, quantum computers are so small that the hand compilation is probably what we'll do for a while. So right now, for example, it's a greedy algorithm where it chooses a node and it lays it out step by step by step. So in particular, it doesn't have the ability to go back and deform this structure and say, I could have done it better, I can see that. It's always edge by edge by edge. So there's a lot of scope for future research to do better. Another thing we need to do is at the moment it's space unconstrained. So it'll lay out the graph, take as much space as it wants. Our next immediate goal, which we'll work over in the next few months, is space constrained compilation, which we're optimistic will be good in so very, very many ways for making everything better. So, yeah.
Why do we want space constraint?
Well, real computers don't have infinite qubits. So you would always start with a piece of hardware. It will have a certain number of qubits. That's it. And you've got to compile to that. Yeah.
Are these circuits the actual ones that you're compiling by hand? Because they look small enough to be handled by, like, you can use SAT solver.
You can use that. Yeah, it doesn't come up with very good options. So the SAT solver has constraints in it. It is a SAT solver, but it requires all of its outputs to be arranged in a certain way. Whereas if you remember my one, I had outputs in all kinds of directions.
Yes.
So it doesn't let you do that. So you can actually get much lower volume than a SAT solver by hand. Because it's written in a certain way. So yeah, again, there's more research to be done to make a SAT solver that does actually get the optimal one. It does not.
Because that one is focused on T-state installation.
It had.
Yeah, the scalpel paper.
Oh,
Yeah, yeah.
that's because the scalpel paper you specify where the location and the orientation of the pipes.
Yeah.
So it doesn't automatically explore that.
That's right. Yeah, exactly.
I'm the first.
It doesn't
author.
automatically explore.
You have to tell it where the outputs are, and once you tell it where the outputs are, that's an enormous constraint, and then it doesn't get the best compilation.
Okay.
So.
Okay.
But in this case, okay, we can talk later.
Yeah. Anyway, so we talked about structure, but right from the beginning we mentioned correlation surfaces, and they're not present here. So the tool does then go in and find the correlation surfaces of the structure, and these are important, and long-term we will need to include them in the compilation process earlier. So right now we don't use the correlation surface as part of compilation. In practice, in a real computation, you must. And you must for the simple reason that when you have non-Clifford nodes, so these pi/4 nodes represent T gates, those T gates, if you look at the correlation surface that tells you, did my T gate do a T or did it do a T dagger? Well, it extends way back in time and touches a whole bunch of things, touches these in the past. This is a time ordering constraint. And so when we compile it, it must be the case that this T gate is placed later than these two. Without the correlation surface, you wouldn't know that. You would mess up the compilation. And then when you went to pound the correlation surface, you go, that's wrong. Right? So the correlation surfaces actually have to be there from the beginning. So this is still an open to-do. A little bit about T-gates. So we want to blast through this. So this is a circuit that can be used to do a T-gate, right? Prepare a T-state, use a bunch of other measurements and gates, maybe include a corrective S-gate, get the right output. Fantastic. Here is the preparation of a T-state using cultivation, just schematic representation. This is also a piece of the puzzle that we need. We need a circuit that can actually do an S-gate. We're definitely not going to go into the details. It's quite a complex circuit that does an S-gate. But what we do want to do, besides just representing as a green block, is look at how these things look in full structure. So let us do that step by step. So we are going to work it through. So here's our circuit. Here's our ancilla preparation, cultivation. We then also have data in, that's here. We then want to do a C0 gate, so it's a blue to red connection. And then we want to do a measurement in the Z basis. Here it is, right there, all right? So that's the first half of the circuit, just up to this purple line. Let's continue. We want the rest of it, all right? Now what we want to do is we want to have the ability to do either an S gate or not. And we're going to initially do that by saying, well, let's either do an X basis measurement, which removes this and just teleports the data down, or a Y basis measurement. So it's a choice. Whichever one we choose to do, if we put this top surface to be blue, what do you think that does? It makes this whole protrusion topologically trivial, and we get a Y basis measurement. If we make this red, it makes it not trivial. We can't reduce it, and this gate doesn't get used. So this is how we can choose with a single layer of gates. Do I not do a physical layer of Hadamard gates, get a different logical measurement, and very quickly decide, am I doing my S-gate, am I not? And we can build on that to have the full structure where we have the T-state prepared, the C0 gate, our data in, Z-basis measurement, which decides whether we color this blue or red and do either an X-basis measurement or a Y-basis measurement. And now we can get busy compressing and manipulating that, because this is clearly not an optimal structure. So first thing we can do is we can just push in these protrusions. They are topologically trivial. We don't need them, all right? We can simplify those structures. They don't need to go up and down and around. They can just go down, all right? Make them simpler. We obviously don't need all of this length, so we can drag this one all the way down, all right? And then we have a kind of giraffe that doesn't need to be so long, right? Drag this whole thing down. It's all still the same computation. Rearrange it. And then you can ask yourself, do I really need to do this later? Well, no, do it first. And that allows you to make an even quicker decision. So this is how you would do a T-gate in lattice surgery. Prepare your T-state. There will be a correlation surface that does a little U-bend around here. And the parity of those corrected measurements will tell you what color this cap should be, red or blue. If it's red, we're doing an X-basis measurement. We are not doing the Y-basis measurement. If it's blue, it's topologically trivial. This doesn't do anything, and we will do a Y-basis measurement. Question?
Yeah, so where, beyond the diagram, are you able to keep track of basically which measurement informed the following measurement choice?
Yeah. So you definitely need in the code to have this correlation surface explicitly connected to what the color will be. So, obviously you have a data structure in there. I'm not sure whether that answers your question.
I think so, and maybe the diagram is insufficient for conveying that.
That's right, yeah. So you definitely need well, we can talk about that explicitly. That's in fact the next slide. So step by step, let's translate that. So we have 2 blue nodes, a red node, and then we have this white node, which is we don't know what color it is yet. All right, so there it is, explicitly. Same thing as a ZX graph. There is an explicit correlation surface right here, and this controls what color you make that, right? Is it red or blue? So yes, you need a graph structure that has correlation surfaces and nodes whose color depends on correlation surfaces. Yeah. All right, but once you have that, you have the ability to then work through how all of those correlation surfaces propagate through and see that the choice here determines whether or not you are sampling this node. So when we put a blue node here, which equates to an X basis logical measurement, this is what dominates the choice. And you might sit there and say, hang on, this is same color red, couldn't I have gone this way? And the answer is, well, no, because when a red correlation surface, an X correlation surface hits a Y basis node, this can only terminate Y. It means it spits out Z, and when this comes back, you'll find that it has to go in both directions, and blue can't terminate on the same color. All right, so this is a forbidden direction. So we didn't have a choice. We could never go down that path in the first place. This was, in fact, the only direction that red correlation surface was allowed to go. All right, so...
Wait a second. So it seems like in your mind you have an assignment of time ordering.
In here you definitely do, yeah. This node has to be later than this correlation surface.
But you don't, is there a reason that you don't write that on the diagram, include that as a part of the diagram?
So I could add more lines to the diagram.
Or like numbers? Like
Yeah. But fundamentally, when you see this correlation surface, right, or very specifically this correlation surface, the thing that needs to be encoded in tqec is that every part of this correlation surface must be in the past of this node. And that is all. Yeah, that's the only thing that needs to be true. Yep. Any other questions about that? Go ahead.
I was sort of on board until the green node went the other direction,
Yeah.
right? So it's not a state generating node, right? You came at it from a measurement perspective, right?
Yeah. So originally it was a Y basis measurement,
Right. Yes.
and now it's become a Y state preparation.
Full thinking.
Yeah.
Okay, on board.
That's right. Yeah, the green node is not truly topologically deformable. It only has 2 orientations, either straight up or straight down. And then it has those 2 rotations. At the moment, there is no version of it on its side. In principle, there could be, but the circuit's never been worked out. Talking to Craig Gidney, he says he's tried, he's just not found a good version of it. Right.
So, awesome.
Yeah.
Does this tqec tool yell at you when you violate those?
Yeah, it wouldn't let you do
What's that?
that. It wouldn't let you put it in on a sideways. So, yeah. So once you build something in SketchUp and then import it into tqec, it will tell you, hey, that's not allowed.
Can we
Like that.
just make sure? I don't think I said that so well. So the time ordering of like this surface needs to be.
So the time ordering of correlation surfaces and nodes is still future work.
Okay.
Yeah, yeah. So at the moment, it's all Clifford, and for that, you can find the correlation surfaces after the fact. Yeah.
Yeah.
But this is building the framework of what we will continue to work on moving forward. And if people are excited, hey, come talk to me. I'd love to work with you on them too. So this is a framework for compiling an arbitrary quantum circuit. Yeah. All of these nodes are Clifford. We have our non-Cliffords, and those non-Cliffords look like this. So anytime you see a single node ending in pi/4, well, that's our T-gate, and we've gone explicitly through how you actually do the T-gate. Now, let's look at an algorithm, all right? So let's imagine we're actually doing an algorithm this way. Very simple algorithm, TH. Let's just start with the first T-gate, which we worked out in loving detail. That is here. Now we want to put in the other gates. So here is our output of our T-gate. It goes through a Hadamard gate. And as I want to do, here is the output. Why not go down for a bit? Because it's convenient, it's Clifford. Come back here, we'll go into another T-gate. So that's all this structure out here. And then again, the output can go out here. So this algorithm can be continued in constant time, with the exception of the decisions of what color did I put here, all right? So imagine this just extends arbitrarily. Well, what's the actual sequence that you do? You're going to execute almost the entire structure, but there's going to be a correlation surface that goes through these bands. And the parity of that corrected correlation surface will tell us what color should be done here. And only when that is known, which takes a certain amount of time, maybe it takes 10 microseconds, maybe it takes 100 microseconds, maybe it takes a millisecond, depends how good you are at doing your classical processing. It depends on how large is the code distance, how hard is it to decode, how advanced is your decoder. So this height depends on your decoder. Let's just imagine it's 10 microseconds for argument's sake. Only when this color is determined can we know what our next T-gate did, because it is the parity of the correlation surface that does this hue, but let's follow it through. So it's a blue correlation surface, it comes through here, it goes up here, it becomes a red correlation surface, it goes to here. This is a blue node, it's the opposite color, so it goes in every direction. It goes both down in the past and across here. This is another blue node, so it goes down into the past and across here. This is a red node, it cannot terminate down here, it must go up this way, dependent on what the color is. So until we actually have chosen the color here, we don't know what the full set of measurements is that's going to determine whether this did a T or a T dagger gate. So we get a time ordering. First this, then classical processing to determine this color. Only then do we know whether this did a T or T dagger gate, and only then can we do the classical processing to determine the color of the next one, which is deliberately bigger. And this continues. So this becomes an explicit 3D realization of reaction-limited quantum computation. You can build your whole algorithm, if you wish, constant logarithmic depth, if you think about it, because these things have logarithmic depth for the code distance. Anyway, but I'll abuse that and say constant structure, implement any algorithm, because any algorithm can be split into layers of non-Clifford and Clifford, and then all you need to do is do the necessary classical processing to determine the bases of specific logical measurements as you rip through that. Any questions about that? Yeah.
So when you look at the thing on the left, that's got an explicit in and out.
Yeah. I mean, this, again, this has an explicit in and out. That in is here, is in, and here is out. Yeah. Yes?
Yeah, so now there's Cliffords and non-Cliffords, and the Cliffords, we can deform, but there is an explicit time ordering that can be enforced for the non-Cliffords.
Yes.
And I guess from this diagram, you just have to know that there's a time ordering, or is there any way to look at this diagram as is and realize what the time order, like which T-gate comes first?
Sure. You could, because you could certainly reduce this structure back to a ZX graph and then analyze it. So physics does that. It'll take the ZX graph and it'll follow those correlation surfaces backwards in time. So yes, you could do that. But yeah, here it's mostly recognizing that this whole thing is a T-gate and it's this correlation that controls this surface. But yeah, you will definitely, of course, in a code base, explicitly put that in. This surface is dependent on that correlation surface.
So in deciding what this thing does, you have to do a bunch of processing, right?
Yeah.
Is that something that you can compile in advance so
Yes.
that the moment you have the, what happened at 2, you can then immediately determine what happens at 3, or does that take time?
So this structure would in general be compiled in advance with some caveats. Cultivation is not a deterministic process, right? And so then you have to ask yourself, how are you going to handle that? So one way you could handle it is simply delay everything when a cultivation takes too long, all right? Which would be fine, to be honest. For this particular type of thing, would be fine. Other ways you could imagine of having a cultivation farm and then having dynamic routing. So there are many ways you could cope with it. In this particular picture, you should not assume that this crossbar is done at a fixed time, because this result of cultivation is not at a fixed time. But hopefully it's clear how you would deform this dynamically to cope with that. So yeah, you could only proceed to the next T gate when the T state is available, but it's a heralded event.
But the point is, you would not have to take your structure and And when the measurement comes, then go through all this analysis and code. This would be done once, and you can in principle put this on something fast.
Sure. I mean, to elaborate on that, you could do that in principle.
Yes.
But of course, it would be harder, right? Wherever you can pre-compile it and then just run it and only have very simple deformations, this is clearly a much easier programming goal than doing something more dynamic, which is, let's just compile the whole ZX graph on the fly. When we get the T-gate here, we'll patch it in. I mean, you could in principle do that, but I mean, and if you feel up to that challenge, please talk to me. Alrighty, so we are just about at time, and this is basically the last slide. So we can't do universal computation yet, but in terms of simulating, we use STEM, which is all Clifford, but there are some great results coming out now of people that are pushing non-Clifford large-scale simulations further and further. You can definitely use the tool as it is to analyze a Clifford circuit. It will take your structure that you've lovingly compiled, find all the correlation surfaces, simulate them, give you the logical error rate of each and every correlation surface, and if you add all those numbers up, you then get the logical error rate of your structure. So in summary, what is TQEC? It's over 1,000-person community, of which we have about 25 people that are actively coding. Everyone is welcome, and we really stress the everyone. Wherever you may be in the world, whatever your profession is, if you are interested, we will find you a job to do. There's always work for everyone. We do need some experts on some of the more complicated stuff. You know, I can't give cultivation to someone who has never done quantum before. It's too complex. But nevertheless, I stand by the statement that everyone's welcome. Come and join. It's a lot of fun. All right, and we're at time. Thank you.